Question number 1. If A and B, they both belong to set of real numbers, and you're given that A plus B is equal to 0, you have just to prove that A is equal to minus B. This is not a very difficult or very important question from paper point of view. However, we will solve it out. You're given that A plus B is equal to 0, and this is given. And you're also given that A and B belong to set of real numbers. They belong to set of real numbers, and every real number has its additive inverse in the set of real numbers, and therefore there exists the additive inverse of this number B, that is minus B, and it must belong to set of real numbers. You can add this additive inverse on the both sides of this equation number A. The result is A plus B plus additive inverse of B is equal to 0 plus additive inverse of B. Next, you will make the use of property that when an additive inverse is added into its corresponding number, the result is an additive identity, that is 0 plus minus B. Next, when an additive identity is added into a real number, when an additive identity of set of real numbers is added into a real number, the number is not acted by that additive identity. Therefore you will get the same number back, A is equal to, and by using the same property here you get minus B. This was what you had to prove. Question number 2 is quite similar to it, and it is not very important from paper point of view. Therefore, I will directly move to question number 3. In question number 3, you're asked to prove that absolute value of A absolute value minus B absolute value is less than or equal to absolute value of A minus B, where A and B are both in the set of real numbers. You can write A absolute value to be equal to A minus B plus B, and you can rewrite it as mod of A is equal to mod of A minus B plus B. Next, we will make use of this inequality. A plus B is less than or equal to mod of A plus mod of B. By making use of this inequality here, we get mod of A is less than or equal to mod of A minus B plus mod of B. You have to remove this plus B from here, therefore you will have to add its additive inverse on both sides. Again, the result of plus B and minus B is an additive identity, therefore we will simply cancel them. The result is mod of A minus mod of B is less than or equal to mod of B minus B, and this is, let me term it as equation number 1. We will make the same procedure to absolute value of B. Absolute value of B is equal to B minus A plus A. Again, by making use of this inequality on this equation, we get b to be less than or equal to mod of b minus a plus mod of a. You will have to remove this from here, and you get mod of b minus mod of a is less than or equal to mod of b minus a plus mod of a minus mod of a. Again, the result of this is a 0. Therefore, we get mod of b minus mod of a is less than or equal to mod of b minus a. Next, you have to find out a form like this one, a minus b and a minus b on both sides. Therefore, you will have to take minus as a common from here. You get and you will also make minus common from here. Next, note that mod of minus a is equal to mod of a. These all of inequalities and this relation are done in the articles of exercise 1.1. So therefore you will have to review them before understanding, before watching out this lecture. This minus sign is immaterial to this absolute value, therefore it is removed simply. We will simply remove it from here. We get a minus b, mod of a minus mod of b. Next, you have to remove this minus sign from here, therefore you will have to multiply a minus 1 from on both sides, and by doing so you get a minus b is greater than or equal to negative of a minus b. Note that when an equality, for example a is less than minus b, is multiplied by a negative number, for example minus 1, the equality sign simply reverses. Name this equation as equation number 2. Look out at equation number 1. It is mod of a minus mod of b is less than or equal to a minus b. This inequality is also similar to it, mod of a minus mod of b. Here it is greater than or equal to, and there was negative less than or equal to, and it is negative here, and it is positive a minus b mod here. Okay, by combining them you get this equation is mod of a minus mod of b is less than or equal to a minus b absolute value of a minus b, and in this equation it is written that mod of a minus mod of b is greater than or equal to negative times of a minus b, or you can also write that minus a minus b is less than or equal to mod of a minus mod of b. This can also be written as negative of a minus b is less than or equal to mod of a minus mod of b. Now by combining this equation and this equation, you simply get this is greater than or equal to negative of a minus b. I think that it is quite clear to you. Now we will also make a use of final relation, and this relation is given at the page number 4, and it is property number 4, that this is very useful and very important property, that if absolute value of x is less than a, then minus a is less than x and x is less than a. We will make use of this relation, mod of x is less than a, then minus a is less than x is less than, positive way. This is the similar expression. It is written that this is less than this and this is less than positive of this, like this one. Therefore we will get the central the central element, this one, its absolute value to be less than or equal to this one. Therefore we get absolute value of a minus b is less than or equal to absolute value of a minus absolute value of b is less than or equal to absolute value of a minus b. This was what you had to prove. Question number 4. Express 3 less than x less than 7 in modulus notation. This is quite important and very simple question. You're given that 3 is less than x, which is less than 7. Note that x less than a implies minus a is less than x less than a. This is property number 4 on the page number 4 of your text. So by making use of this inequality, you get another inequality. For example, x minus a is less than b. Mod of x minus a is less than b. This implies, by making use of this relation, you get x minus a greater than minus b and this one less than b. You need x in the center, therefore we will remove minus a from here, which can be done by adding b in all of the sides of inequality. By adding a in all of the sides of this inequality. So minus b plus a is less than x minus a plus a is less than b plus a, which in turns a minus b is less than x, because a and a are cancelled out, is less than a plus b. Name it by inequality number 1 and name it by inequality number 2. From this we have seen that when inequality 1 holds, then we get inequality number 2. Compare your original inequality, let a term is an inequality number capital A. Compare this with this, you get a minus b is equal to 3, a plus b is equal to 7. So we will write, comparing inequality A and inequality 2, we get a plus b is equal to 7 and a minus b is equal to 3. From here a is equal to 3 plus b. Put this value of a into this equation, you get 3 plus b is equal to 7. This means 2b is equal to 7 minus 3 is equal to 4. That is, b is equal to 4. 4 divided by 2, this is 2. So b is equal to 2. Put this value of b is equal to b, that is 2. Here you get a is equal to 3 plus 2, that is a is equal to 5. So you have taken out the values of a and b by solving this equation and this equation simultaneously. Now put these values back into inequality number 1. You simply get mod of x minus a, that is 5, is less than b, that is 2. This was what you needed. Answer of question number 4. Now we will solve the question number 5. This is quite similar to this equation, this question. In question number 5, you're given that let delta be greater than 0 and a is in the set of real numbers. You have to prove that a minus delta is less than x is less than a plus delta if and only if mod of x minus a is less than delta. For this equation, because there is if and only if, so you will first suppose that this is true and you will prove this one. and then you will suppose this one and you will have to prove this one. First we will suppose that a minus delta is less than x is less than a plus delta. Question number 5 solution. Let a minus delta is less than x is less than a plus delta. From this, since you need x minus a in the absolute value, therefore we will subtract minus a in all of the side of this equation. A minus delta minus a less than x minus a and a plus delta minus a. We have subtracted a from all of the sides of this inequality, previous inequality. You get, this is cancelled by this and this one is cancelled by this. You simply get minus delta is less than x minus a is less than delta. What is this? This is mod of x minus a is less than delta, because from property 4 on page number 4, mod of x is less than a implies minus a is less than x is less than a. We have simply used this inequality. This is what we needed to prove. Now we will suppose this is true, that is x minus a is less than delta. Now by making use of this definition, you get x minus a greater than minus delta and less than plus delta. You have to remove minus a from here, therefore you will add a on all of the sides of this inequality, x minus a plus a, delta plus a, and the result is a minus delta is less than x is less than delta plus a or a plus delta. So you have done both of the things. You have first supposed this assertion and you proved this one, and next you proved you supposed this one to be true and you proved this one. Therefore you have done all of the things, and this one is called the converse. Thus this implies this was what you needed to prove. Question number 6. Give an example of a set of rational numbers which is bounded above but does not have a rational supremum. Be very sure that you know what is meant by upper bound, lower bound, and supremum and infimum. These definitions are provided at page number 5, the completeness properties of set of real numbers, and there are given the definitions of lower bound, upper bound, infimum and supremum. So before watching out the video, you must understand these concepts given at page number 5. According to the requirement of our question, we have to find out a set of rational numbers which is bounded above. First, it must be bounded above, and since it is bounded above, so it must have a it must have a supremum. According to the requirement, the supremum must not be a rational number. Here, for example, we can choose a set A, and it is defined by x. All of the elements of this set are represented by x, such that x are members of Q, where Q is rational set of rational numbers. All of the X, it means all of the elements of this set are in set of rational numbers. Okay. Secondly, we need that this must be bounded from above. We can take, for example, x square less than any number, for example 2. Now this set is clearly bounded from above. What are its upper bounds? We can see easily x square is less than 2. By squaring both sides we get x is less than square root 2. This means that square root 2 is clearly an upper bound of this set, and all of the numbers greater than square root 2 are also the upper bounds of this set. Therefore, this set is bounded from above. Note that the smallest upper bound is square root 2. Therefore, this square root 2 is the supremum. So this set has a supremum. Clearly, you will write clearly, this set is bounded from above and x is equal to square root 2 is the supremum of A, the set. And note that what is the supremum of this set? The supremum of this set is square root 2, and this is an irrational number. Note that the set is containing all of the rational numbers whose squares are less than 2, and we have noticed that the supremum, the least upper bound of this set is x is equal to square root 2, and this is an irrational number. This is the requirement of our question. Similarly, we can give some other examples in which, for example, a set B, we can take out set B in which all of the elements are rational numbers, but their squares are less than 3. What is the upper bound of this set? Upper bounds are all of the sets that are less than square root 3. Therefore, square root 3 is a supremum of this set, and this is again a rational number. Similarly, we can define them by x square less than 5, all of the x members of rational numbers in which their squares are less than 5. This is also an example of the required set, because square root 5 is the least upper bound, that is supremum of this set, and therefore this set is also the required set, because the square root 5 is the irrational supremum, not a rational supremum. Similarly, by generally speaking, we can take out a set C which is in set of rational numbers, and such that their squares are less than p, where p is a prime number, where p is prime. Then square root p is the supremum of this set, and this is not a rational number, because any prime number in the square root yields an irrational number. Therefore, it was what that was required in this question. So, from paper point of view, the question from here to here is enough for you. This is the answer of this question. I have just generalized the solution of this question. You can also write out this step and these steps. However, it is enough to write from here to here. Solve each of the following inequalities in problem 7 through 15. Question number 7 is absolute value of 2x plus 5 is greater than 2 minus 5x. Absolute value. To understand these questions, be sure that you have already understood the definitions of intervals given at the page number 6 of your book, and then inequalities, the definition of inequalities that are here at the same page, and the method of boundary numbers given at the page number 7, and the example number 3, example number 4, and example number 5 given at the page number 7, 8 and 9. Now we will solve out question number 7. Question number 7, it is absolute value of 2x plus 5 is greater than 2 minus 5x, absolute value. Well, the first we have to associate an equation to this inequality. So the associated equation is 2x plus 5. This sign is removed, it is replaced by equal sign, equality sign, equal 2 minus 5x, and there are absolute values. This equation can easily be solved by removing the absolute sign. We get a plus and minus. Next we will solve out this. We get two equations from here. One is 2x plus 5 is equal to plus 2 minus 5x, and the other one is 2x plus 5 is equal to negative times 2 minus 5x. We will first solve this equation. From this equation we get 7x is equal to minus 3. So x is equal to minus 3 divided by 7, and minus 3 divided by 7 is equal to minus 4.43 approximately. Similarly, we will solve out this. This is plus 5x when taken here. It becomes minus 3x is equal to minus 7, which gives 7 divided by 3, and 7 divided by 3 is approximately equal to 2.33 and up to so on. Now these two are the boundary numbers. These are called the boundary numbers. Now we will draw a real line. We will draw a real line, and origin is placed at the center. One boundary point is minus 0.43. Here it is minus 1, and minus 0.43 becomes somewhere between here, and this is minus 0.43, which is 3 by 7. And similarly 2.33, 7 by 3, this is 1 and this is 2 and this is 3. 2.33 lies somewhere between 2 and 3, and it would be here, for example, and it is 7 divided by 3. We highlight these two boundary points. Now we have three regions. This is minus infinity and this is positive infinity. The three regions are, one is starts from negative infinity and it ends at minus 3 by 7, and the second region is it starts from minus 3 by 7 up to 7 by 3, and the third region is it starts from 7 by 3 and it ends at the positive infinity. We call this region as region number A and this region as region number B and this region as region number C. We have named these regions A, B and C respectively. Now we will take test points from these regions and we will put them in our inequality number 1. Region A is we will check if this region should come in the solution or not, and this can be accomplished by taking a test point in this region. One of the test points in this region is clear to be minus 1, so we will put a minus 1 in the inequality, given inequality, that was 2x and x is replaced by minus 1, 2x plus 5 greater than 2 minus 5x, and in place of x we will write minus 1. Now check for it. This is minus 2 plus 5 absolute value greater than 2 plus 5 absolute value, and the answer of this is 3 absolute value greater than 7 absolute value, which means 3 is greater than 7. This is not true. This is false. So therefore the region A does not satisfy the solution region, and it does not happen to be the solution region. So solution region A is not in solution. We will write region A is not in solution. Now by the same process we will check the region number B. We will also take a test point from this region. Note that a test point between minus 3 by 7 and 7 by 3, which are the boundaries of region B, one of the test points is 0. Similarly, one test point is 1 and another one is 2. Simplest one is the 0, so we will take it as a test point. You can also take 1 or you can also take point 2 as a boundary point. So we will test x is equal to 0 in this region. When you put x is equal to 0 in your inequality, it becomes 2 times 0 plus 5 absolute value is greater than absolute value 2 minus 5 times 0 absolute value, and this is absolute value 5 greater than absolute value of plus 2, which means 5 is greater than 2, and therefore it is true Therefore, the region B is in the solution set. Finally, we will check out this region, which is region C. It starts from 7 by 3 and it ends at plus infinity. It means that it has no upper bound and it has lower bounds. One of the test point is 3, another one is 4, 5, 6. I will take 3 as a test point. We will put x is equal to 3 in this inequality number 1. Region C. Test x is equal to 3, and you will put it into inequality number 1, that is your given inequality. 2x plus 5 is greater than 2 minus 5 times x. This is 6 plus 5, this is 11 absolute value greater than 2 minus 15, which is minus 13, and minus 13 is, when taken its absolute value, it becomes positive. 11 is greater than 13. This is not true, false. Since only one region satisfies our inequality, that was the region number B, and only this region is in the solution set, and this region starts from minus 3 by 7 and it ends at 7 by 3. So the solution region is all of the points coming between this point and this point. Note that these two points are called the boundary points, and since in given inequality there is no equal sign, only greater than sign, and for only greater than or smaller than signs, these boundary points are not included in the solution. Therefore, the solution is all of the points coming between these points. Therefore, we will write the solution as solution set is all of the x where x are on the real line or the members of real numbers, such that minus 3 by 7 is less than x, which is less than 7 by 3. Minus 3 by 7 is less than x, which is less than 7 by 3. This solution can also be written as minus 3 by 7 and 7 by 3. Note that parentheses denote the open interval, and open interval can also be written as minus 3 by 7, 7 by 3, like that. You will have to look out at page number 6 for different definitions of intervals. I think that it was quite helpful to you. This is the answer of your question. Question number 8. You have to solve the inequality. Absolute value of x plus 8 divided by 12 less than x minus 1 whole divided by 10. X plus 8 divided by 12 absolute value less than x minus 1 divided by 10. Associated equation which is associated to this inequality. Associated equation is x plus 8 divided by 12 is equal to x minus 1 whole divided by 10. The solution of this equation, there is an absolute value here. The solution of this equation is x is equal to plus 46 and x is equal to negative 3.1, and these two are the boundary points. These are called boundary points. Here is negative infinity, there is positive infinity, and here is center of this real number, which is also called the origin, and 0 of this real number line. Next, we have to place these points here. Positive 46 comes out to be somewhere here, and negative 3.1 comes out to be somewhere here. Nice, 3.1. This region is starting from negative infinity and ending at minus 3.1, and this is region B that starts from minus 3.1 and it ends at 46, and this is third region, that is C, that starts from 46 and ends at positive infinity. We will check all the first region A. Look that one of the point in this region is minus 4, so you can check out x is equal to minus 4, and you will simply put it in your inequality and call it inequality number 1. When you will put x is equal to minus 4 is there, you will get minus 4 plus 8 divided by 12 less than minus 4 minus 1 divided by 10. This is 4 divided by 12 less than minus 5 divided by 10. Note that this is absolute value, therefore it generates positive numbers. This is positive and this number is negative. This obviously means that this is greater than this one, not smaller than this one. This is not true, and we will say that this is false. Now we will check out the second region, that is minus 3.1 up to 46. One of the point in this region between this and this is, one of the points is this 0. So we will put 0 in this region. Test x is equal to 0. When you will put it in your inequality, given in inequality, you get 0 plus 8 divided by 12 less than 0 minus 1 divided by 10. This is again a positive number, and this is negative number, therefore it is also false, and this region is not in the solution. Finally, we will check out the region C. And in the region C, it starts from 46 and ends at positive infinity. There is a point 50 between those, so we will put 50 here. We get 50 plus 8 divided by 12 less than 50 minus 1 divided by 10. 50 plus 8, 58 divided by 12, absolute value less than 49 divided by 10. This is 4.9, and what is its answer? 58 divided by 12, this is equal to 4.83, and this number is obviously smaller than this, therefore it is true. So the only region that is satisfying the given inequality is region number C. Therefore, this region is the solution. So the solution set is, it starts from 46 and it ends at positive infinity. Note that 46 cannot be included in the solution, therefore the interval is open from here, and positive infinity is also not a real number. It is, the interval is kept open from here. I think it was quite clear to you, and this solution can also be written as or every x is member of real numbers where x are greater than 46. Question number 9 is absolute value of x plus absolute value of x minus 1 is greater than 1. The associated equation is it as equation number equation 1. The associated equation is this one, and term is at equation 2. When the absolute sign is removed, we get plus minus. Similarly, plus minus x minus 1 is equal to 1. Note that there could be 4 equations. We can form 4 equations from this one. The first one is take this positive x and this expression as positive. Take plus sign from here and plus sign from here. You get the equation x plus x minus 1 is equal to 1. This is first equation. Name it equation A. Similarly, take minus from here and minus from here. You get minus x minus x minus 1 is equal to 1. Name it as equation number B. Now take plus x from here and minus this expression from here. Plus x minus x minus 1 is equal to 1. This is equation number C. And take minus x from here and plus this expression from here. Minus x plus x minus 1 is equal to 1. And name it as equation number D. Now you have to solve this equation. You will get x is cancelled by this x. You get 1 is equal to 1. You get 1 is equal to 1, which gives us no information. It means that we cannot find out any boundary number from this one. Similarly, when you will solve equation number D, this minus x1 is cancelled, x is cancelled with plus x, and you get minus 1 is equal to 1, which is false, impossible. So this one also gives no information about the boundary points. Therefore, we have only 3 equations. One is equation A and the other is equation B. If you solve this equation, you will get 2x plus 2x is equal to 2. 2x is equal to 2. And when you will solve the second equation, you will get minus 2x and is equal to 0. From here, one of the boundary point is x is equal to 1, and from here one of the boundary point is x is equal to 0. So these are 2 of the boundary points. Now we will draw the real numbers line, negative infinity here, positive infinity here, and 0x center. One of the boundary point is 1 and the second boundary point is 0. First region is A and it is from negative infinity to 0. Second region is B and it is from 0 to positive 1. And the third region is C and it is from positive 1 to positive infinity. Now you will check region A. Take a test point in this region. One of the test points is here, for example, -1. You will simply substitute this in the given inequality. The given inequality is the inequality 1. You will simply put this -1 in this inequality. You will get absolute value of -1 plus absolute value of -1 is greater than 1. This is 1 plus this is -2 absolute value greater than 1, and this is 1 plus 2 greater than 1, which is 2. So it means that this region from infinity to 0 is included in the solution. Secondly, we will check region number B. In region B, one of the point is, we have to take one of the points between 0 and 1. It can be x is equal to 1 by 2. When you will put x is equal to 1 by 2, in the given inequality, the given inequality will become 1 by 2 absolute value plus 1 by 2 minus 1 is greater than 1, and this is 1 by 2 plus this is minus 1 by 2 absolute value greater than 1. 1 is greater than 1. You get this, which is false, because 1 is equal to 1. It is not greater than 1. So therefore region B does not qualifies to be the solution region. Finally, we will check the region C. One of the point in the region C is x is equal to, for example, 2. When you will put this 2 in the given inequality, you get mod of 2 plus 2 minus 1 greater than 1, and this is 2 plus this is 1 greater than 1, and yes, it is 2. So we have 2 points as the we have 2 regions as the solution. One is the region A, which starts from minus infinity and ends at 0, and the second one is the region C that starts from 1 to positive infinity, and therefore your solution is, you can write it here, your solution is, solution set is equal to 2 of the intervals we have. One is minus infinity to 0, and note that this 0 cannot be included in the solution because the given inequality contains only greater than sign, or if there were the greater than or equal to sign, then we could include 0. Okay, the next one was C region. In the solution, it starts from 1 to positive infinity. We will simply make union of these two intervals from positive 1 to positive infinity. This is the solution that we needed. Question number 10 is pretty simpler, and it is, question 10 is 12x square minus 25x plus 12 greater than 0. Associated equation is 12x square minus 25x plus 12 is equal to 0, and after solving this equation by using quadratic formula, or by factorization, you will get x is equal to, one is 4 by 3 and the other one is 3 by 4. These are two of the boundary points. We will write it here. This is negative infinity, positive infinity, 0. 4 divided by 3 is equal to 1.33. This is 1 and this is 2. 1.33 is somewhere here, 1.33. And 3 by 4, 3 divided by 4 is equal to 0.75, which lies somewhere here. This is 0.75. So we have three regions. One is from minus infinity to 0.75 or 4 by 3, sorry 3 by 4. So this is region A, and the second region is from here to here. This is region B, and the third region is from here to positive infinity, and this is region C. Test points. Check for region A. One of the test points in region A is x is equal to 0, and when you will put it into given inequality, you will get 12 0 square minus 25 times 0 plus 12 greater than 0, which is true. So region A from minus infinity to 3 by 4 is included in the solution. Similarly, now we will check the region number B. In this region, one of the test points is 1. You can put x is equal to 1 as a test point. You get 12 times 1 square minus 25 times 1 plus 12 greater than 0. And answer of it is 24 minus 25, which is minus 1, greater than 0. No, this is false. So this is not in the solution region. The final one is region number C. And region C includes 1.33 up to positive infinity. Therefore 2 lies in this region. We will take x is equal to 2 as a test point of this region, and we will substitute it into our given inequality, that was this one. After putting it here, you get times 2 plus 12 greater than 0, and this is true. And the solution is, solution set is equal to union of this region and this region, union of region A and region C, and the solution thus becomes minus infinity to 0.75 or 3 by 4 union C, and this is positive infinity to 4 by 3, 4 by 3 to positive infinity. I think that it was quite clear to you. Thanks for watching.